And I want to introduce you to a new feature that's available as of StanCon2018, which is the nonlinear algebraic solver. So what does it do? It's fairly straightforward. So let's say we have a function that depends on x and maybe other arguments. We want to find x star such that f of x star goes to 0. And of course, this has a lot of applications because whenever you have some algebraic equation or some equality, you can just take one side of the equation, put it on the other side, and then you have a function that you want to make go to 0. The applications are in a lot of fields, and the one I'm going to focus on is biomedicine, and especially characterizing patients at steady states. This is not only an application, but actually one of the motivating problems that made the Stan developers come up with this new function. So oftentimes the question we're asking when we're doing those biomedical models, in particular in pharmacometrics, which is quantitative pharmacology, is how does a patient react to treatment? Usually there's two steps to that. How does a drug diffuse inside a patient's body? And once the drug is in the patient's body, what are its effects? So maybe it's targeting a disease. It may also have some undesired toxic side effects. Today I'm only going to focus on drug diffusion, just to keep it simple. And this is kind of your archetype pharmacometrics model where you have a drug that enters the body through the gut. So if the patient is taking the drug orally, and then it's going to diffuse into various compartments. So we've divided the human body into these compartments that corresponds to organs and circulatory systems, such as the blood and maybe other tissues. So the drug goes from the gut into one compartment, so maybe the blood, and then it diffuses into another compartment, circulates back and forth, and then it gets cleared out of the body. And this kind of diffusion process is often described by a system of differential equations. So here in this case we have 3 ordinary differential equations. But this diffusion model doesn't tell the whole story. It tells us what happens once the drug is inside the body. It doesn't tell us anything about the treatment. So we need to think very carefully about what is the treatment the patient is receiving. In this example, we're going to consider a very simple treatment, which is the case where a patient takes a pill at a regular time interval, and so the treatment is going to look something like that. It's going to undergo cycles that are going to repeat themselves. At T0, the cycle begins. The patient receives a dose, so you're kind of going to have a spike in the drug mass inside the patient's gut. Then the drug is going to diffuse in the patient's body according to the differential equations that I presented before, and then the next cycle begins. So what does data we collect during clinical trials maybe look like? Well, if I'm measuring the drug concentration inside the blood, I may have something like this, where clearly you see that there are different cycles repeating itself. I start at the beginning of the treatment, then there's a spike because the patient is taking a pill, it gets cleared out of the body, and then there's another spike. And what you may notice is that between cycle, there's kind of a increase in the drug concentration as the patient takes more and more of those drug doses, right? So especially if I look at the drug concentration at the beginning of each cycle, it increases on average. However, as time goes on, it kind of plateaus, right? And what we expect in a lot of cases is that the patient is going to reach some kind of equilibrium or steady state. And we are interested in modeling these steady states because oftentimes a patient is going to be taking a treatment for an extended period of time, so we want to model what is this going to look like. Maybe the patient has a disease that cannot be cured but only contained, so they're going to be taking that treatment for an indefinite amount of time. And so if I have a steady state, it's going to look something like that. You have some minor variation, which is due to noise between cycles, but it's pretty much the same between cycles. And there are 2 ways in which we can model this. One is we simulate a lot of treatments, and then we hope that we reach steady state after simulating a lot of those treatments. Or the more elegant approach, and therefore the much more efficient approach, actually, computationally, is to solve a system of algebraic equation. So if we let y be the drug mass, and here I'm kind of highlighting its dependence on time, be the drug mass vector in the patient's body. So that's going to be the drug mass and all of the compartments of the model, the pharmacometrics model I presented at the beginning. And then we let tau be the interdose interval. So how much time is there between one drug intake and the next drug intake? Then steady state is reached when y of t plus tau is equal to y of t. Or equivalently, I'm going to rewrite this as a root-finding problem when the difference between these two states goes to 0. So, what does the drug mass depend on? Well, it's going to depend on y naught, the initial drug mass, and this is actually, in this particular problem, what I'm going to try and find. Right? This is the unknown to my algebraic equation, and it's going to allow me to characterize the state of the patient at steady state. I have time, then maybe I have model parameters, so these could be the coefficients in my differential equations, or I could also have fixed data. Right? And our goal, just to reiterate it, is we want to find y star, the drug mass at the beginning of a cycle, such that this function goes to 0. But because we're working in STAN, there's actually an augmented root-finding problem that we need to solve. We don't simply need the solution, we also need to calculate derivatives, right? This is how the Hamiltonian Monte Carlo sampler works. The reason it's so efficient is because it's paying attention to the geometry of the parameter of the posterior as it's exploring the parameter space. So I'm going to need to calculate this Jacobian of the solution with respect to the parameters that are going to appear in my function. So I'm not going to develop in detail what is the algorithm that allows you to solve the algebraic equation, but I'll give you a short glimpse because it will motivate some tuning parameters that you as users might find useful. And especially, you need to realize that this solver, it's kind of an optimization algorithm. You give it an initial guess, right? And then it's going to tweak this guess, right? One iteration after the other, and it's going to try and converge to a better guess until it finds an acceptable solution, right? That's kind of your typical numerical solver. And so there are three tuning parameters that kind of regulate this process. One is the relative tolerance. So usually there's some approximation of how close you are to a solution. And you want to be very close to that solution. And so you can tweak the relative tolerance to tell how close you want to be to that solution before the solver considers it has converged to an acceptable solution. There's also the maximum number of steps, right, which is going to put a limit on the number of iterations the solver is going to go through. And one of the reasons you might want to do that is maybe your Markov chain has wandered off into some region, some absurd region of the parameter space, so solving the algebraic equation becomes really, really, really hard. So your solver is not going to converge. You want to stop it at some point and say, all right, look, reject the Metropolis proposal, go back one step, and see if we land in a region of the parameter space where we can actually solve the algebraic equation, right? And then the other thing is the function tolerance. So it's kind of an analog to the absolute tolerance that you have when you're solving differential equations numerically. And it's very simple. We just put our proposed solution inside of F, and we check whether it's close to 0 or not, right, by looking at the norm. All right. The other thing I want to make you aware of is how this Jacobian is calculated. So that's my matrix of derivatives. And it kind of uses what I would call a lemma of the implicit function theorem. But the point is, the Jacobian, which is J star, is equal to a product of two matrices. One of them is Jy, which is the Jacobian matrix of the function f, so the function we want to go to 0, with respect to y, which is the unknown state. And this matrix actually gets inverted. And so that kind of puts some constraints on the problem we're trying to solve, because J sub y needs to be a squared matrix. And essentially what that means is the number of equations in my algebraic solver needs to be the same as the number of unknowns that I'm trying to solve with, right? So you need to have a somewhat well-behaved algebraic equation. Okay, so how would I code this in STAN? So it's a kind of a two-step process. One, I would write down the algebraic equation, and the way I would do that is I would go inside the functions block and would create this new function Here I called it system. It returns a vector. So this vector z, this is what we want to go to 0. And then it takes in my unknown parameters and fixed data that can intervene as coefficients. So this is an example from the Stan user manual, by the way, where it's actually a very simple nonlinear equation. And note that even though xr and xi, which are my fixed data, don't intervene inside the function's body, I still need to declare them because there's kind of a strict signature for the function. Right? That's a constraint when you're using higher order functions inside of Stan. A more sophisticated example that's relevant to the problem in pharmacometrics that I introduced at the beginning is where we have the state of the patient at the beginning of a cycle and the state of a patient at the end of a cycle. And actually inside the function, we're solving a differential equation numerically using the integrate ODE RK45 function. Right? And that's kind of the cool thing that this nonlinear algebraic solver lets you do. You can have a function that's relatively complex. You're going to get the solution, and you're going to get the derivatives. Right? That was kind of the technical feat. I'll say that the problem I presented is actually simple enough that there's an analytical solution to the differential equations. And in the notebook that complements this talk, I actually coded the Stan model both ways. Right, so you have one model that's going to run very fast, and then one model that's going to exemplify the flexibility and the scalability of the algebraic solver. And then how do I call the algebraic solver? Well, the first argument is going to be the name of the function that I defined inside the functions block. Right? Then I'm going to have my initial guess. So I need to provide an initial guess, and this can be important. It's going to make your solver converge faster or converge at all. Right? And then I have my parameters, my data, and then my tuning parameters, the relative tolerance, the function tolerance, and the maximum number of steps. Okay? And I'm just going to say a few things about the initial guess. Really what you want to do is give the solver some idea of what the scale at which you're expecting a solution is. So what I did in the notebook is like, all right, I know what the dose, the drug dose is. I'm going to use that as a scale. It's a little bit naive. A better approach would be to use, to simulate one cycle at the beginning of a treatment, and then you look at the state of the patient, and you're like, well, it's probably an underestimate of the drug mass in the patient's body, but maybe it gives me a good idea of what the scale is. So I'm going to use that. One of the limitations of this is that that guess is going to be parameter dependent, and the way the algebraic solver was implemented in Stan 2.17 is it requires y_init to be only data dependent. So people complained about it on discourse, and guess what? We created an issue on GitHub, and we fixed it. So as of Stan 2.18, you'll be able to pass parameter-dependent initial guesses. There are then also more sophisticated ways of making guesses. There's one program that kind of like, if the solver fails to converge, it actually creates a new guess by simulating a bunch of cycles, and then it plugs in this guess. So I don't know how we could do it in Stan, but I definitely want to think about it if we have a proof of concept to show that this really helps the solver converge. All right, other than that, I can run the Stan model. I get some estimate of my parameters. The Markov chains seem to converge, and then I'm able to fit my data. So this is pretty good. You can try it yourself with the notebook. And finally, I'd like to acknowledge some individuals. Obviously, Bill Gillespie, who was my mentor at Metrum Research Group, the Stan development team. Yeah, very, very moving talk by Dan earlier. It's just been great in terms of mentorship and guiding you and reviewing code and criticizing code. And then we've also received funding from a couple of institutions. Thank you very much.
In your problem, you're solving for the steady state, but you didn't seem to have exploited the fact that you have differential equations there. You could have differentiated, to get your derivatives, you could have differentiated your ODEs, and then, instead of solving algebraic kind of system, in and of itself, you could have exploited the ODEs.
So I think what you're saying is, okay, I have those ODEs, and then I can get the derivatives of those ODEs, and then use that to kind of get the solution. But what happens when your ODE doesn't have a closed form solution, and you're not able to get the derivatives of that, right?
Well, you have automatic differentiation, so I don't know. Is that usable?
So I mean, you know, we kind of use that, right? But and in a way, it kind of happens under the hood. But you know, if you have other method to suggest, like, we should definitely sit down and talk about it.
Here, hold on. That's just it.
If I understood him correctly, he's basically asking whether it does what it does do. That was a terrible sentence, but the ODE solver does take advantage of that. Mm-hmm. So it augments the system of ODEs by taking derivatives of the original system of ODEs to create a larger set of ODEs, so that the resulting solution gives you both the solution to the system as well as the gradient mm-hmm. in one go. Not sure if that's what you were suggesting, but it sort of sounded that way to me. It's with respect to the parameters.
Yeah.
Any others? Come on, don't make me ask one. Oh boy. You got a question, Bill? All right. All right, it's good. Well, let's thank the speaker. Thank you so much.